How many times have you heard someone say that math is fun? And we're not counting our professors or teachers. Mathematics has an unfortunate image of being complex and tiresome with theorems and formulas. I've always regarded this image as a side effect of the way we're taught and introduced to mathematics. Hi, I'm Aarav Goel, and I fancy calling myself a mathematician. I've been in love with math for the longest time, and I just want to introduce you to a part of math which you may not have seen before. By the end of the series, even if you're unconvinced that math is fun, I'm convinced you'll leave having learned something new and interesting. There are intuitive and foundational ideas in mathematics which, in retrospect, feel like common sense. And it's these ideas which I believe are readily useful in everyday life. I've been talking about these very abstractly, so I'll list some out. There's induction, symmetry, invariance, methods of proof like contradiction. Throughout the series, I intend to introduce these ideas to you, but not in a manner where I spout mathematical jargon and detailed rigorous proofs. I wish to build intuition regarding these ideas using games. Now, games is a bit generous because you won't be able to play any of these with more than two players. And once we solve them, you won't be playing these with two players either. Each game consists of a set of rules, usually involving two players, and our objective is to figure out whether any of the players have a winning strategy and what that strategy is. The video lectures essentially delve into a field of mathematics known as combinatorial game theory. Though I will take a rather casual approach to the exposition since the objective isn't mathematical rigor, but it's to introduce a more general audience to ideas in elementary mathematical reasoning which isn't available in the standard school curriculum. Now, there's a question which has been asked to every mathematician at least once, and it's some variation of what's the application or how do you use it. In this case, I do have an answer. And the use case is very simple. It's to develop problem-solving methodologies. The ideas that we use to solve these games can be used heuristically in various fields. The intent of the video lectures is to give you skills which you can use to be a better problem solver. And I also wish to use these to create more exposure to counteract the aforementioned image of mathematics and draw more people to the subject. Let's play a game. Imagine two players, Freddy and Sarah. They have a sack with 17 balls inside of it. The rules are as follows. First, the players move alternately, with Freddy going first. Second, in one move, the players can take out 1, 2, or 3 balls out of the sack. Third, whosoever empties the sack loses the game. So that's the game. And our final objective is to deduce who, if anyone, has a winning strategy and what that strategy is. But before we get to that, maybe we should try an example game. Another thing I'd like to mention is that if at any point you think you can understand where the argument is going, you should pause and try it out for yourself. Now back to the example. Initially, there are 17 marbles inside of the sack. Freddy could take out 2 and then Sarah could take out 3. Now say Freddy takes out 3 again and Sarah takes out 2 and then Freddy takes out 3. At this point there's 4 marbles left in the sack and Sarah realizes that if she takes out 3 marbles she can force Freddy to empty the sack. So Freddy loses. You can try out a few more examples of the game to see if you can understand how the rules work. Now, anytime we're introduced to something new, to a different kind of problem where we aren't sure how to reach the solution, it's a good idea to try simple cases. Before trying to solve the given version of the problem, we try the simplest case we can find and try to build our solution up to the more complex problem. In this, there are 2 places where we can simplify. The first is the number of balls in the sack. Second is the number of balls the players are allowed to take out of the sack in one move. Let me try the simplest case I can think of. That is, if there is 1 ball in the sack and the players are allowed to take out only 1 ball from the sack. Well, in this case, it's Freddy just loses because Freddy is forced to empty the sack. But what if there is 2 balls in the sack? Well, then Freddy just has to take 1 and then Sarah has to take 1 and Sarah loses. Now that I think about it, if there's an odd number of balls, then Freddy loses, and if there's an even number of balls, then Sarah is forced to lose. This is where I'll point out something crucial, which is to be wary of oversimplifications. Sometimes in the process of simplifying, you could go too far and lose the structure of the problem. When this happens, you may not get any useful information as to how to approach the more general case. Like here, in assuming that the players could take out only one ball, I have removed the element of choice, where the players could choose the number of balls they take out. So, to reintroduce that factor, let's consider the case where the players can take out one or two balls out of the sack. Well, in this case, say if there's one ball in the sack, well then Freddy loses. Freddy is forced to empty the sack. If there's two balls in the sack, well then Freddy can choose to take out one ball, after which Sarah loses. Similarly, if there's three balls inside of the sack, then Freddy can take out two of those balls, after which Sarah will be forced to empty the sack, and once again Sarah will lose. But what if there's actually four balls in the sack? Freddy has two possible moves. He can take out one ball and leave three, or he can take out two balls and leave two. In either case, Sarah can win by taking out two balls in the first case and one ball in the second case, after which Freddy will be forced to empty the sack in both cases and Freddy will lose. Here we see another idea. We see that if a player is making a move from a sack with two or three marbles, they can win. These we will call winning states. Also, if a player is making a move from a sack with four balls, then they will lose. Such positions will be called losing states. 4 is losing because all moves from 4 lead to 3 and 2, which are both winning states, and thus the opposite player would win. Similarly, when there are 5 and 6 balls in the sack, well, Freddy can take out 1 or 2 balls out of the sack, respectively, and leave Sarah at the position where there are 4 balls in the sack, which is a losing state for Sarah. Thus, the original states, 5 and 6, are winning for Freddy. Now we can generalize this idea. Say from a state, there is some move which leads to a losing state. That's losing for the opposite player, which means the original state is winning. Similarly, if from a state, all moves lead to winning states, well, then we can't prevent a loss. So the state is a losing state. We can use these ideas to categorize the other cases. Say there are 7 balls in the sack. Well, then both moves lead to either 5 or 6, which are both winning states. So 7 itself is losing. If there's 8 balls in the sack, well, there's a move which takes us to 7. If there's 9, we have a move which takes us to 7. 7 is a losing state. So 8 and 9 are all both winning states. 10, both moves lead to 8 and 9. 8 and 9 are winning states, which means 10 is a losing state. At this point, we could figure out the winning strategy in this case. The losing states are all 3 apart, and we must always leave the opposite player in a losing state. So what we can do is just play the complement of whatever they do. That is, say from a sack of 10 balls, they take out 2 balls, then we take out 1 ball. If they take out 1 ball, then we take out 2 balls. So that the net effect of the 2 moves is to decrease the number of balls in the sack by 3, and the opposite player is once again at a losing state. We could generalize the same idea to the original problem. The only difference is that now the players can take out 1, 2 or 3 balls out of the sack. We once again categorize winning and losing states. So 1 is losing because Freddy is supposed to empty the sack. From 2, 3 and 4 there is a move which leads to 1. So 2, 3 and 4 are all winning. From 5, all 3 moves lead to 4, 3, 2, which are all losing states, winning states. So 5 must be losing. 6, 7, 8. There is a move which takes us to 5, which is a losing state. So 6, 7, 8 are themselves winning. 9, all 3 moves lead to winning states. So 9 is losing. And 10, 11, 12. There is a move which leads us to a losing state, 9. So these 3 are winning. You can see that the losing states are all 4 apart. And that makes sense. Because one individual player could never cross the gap of 4 in just a move. So the opposite player can always take out the complement. So if they play 1, 2 or 3, the other player can take out 3, 2 and 1. So that the net effect of the 2 moves is to remove 4 balls from the sack. Now, the original problem had 70 balls. The losing states are 1, that 4, 5, plus 4, 9, plus 4, 13, and adding 4 again, 17. So Freddy is initially in a losing state. Thus, as long as Sarah plays optimally, Freddy will lose and Sarah will win. Notice that all the losing states are 1 more than a multiple of 4, which makes sense because all the losing states are 4 apart. Now, here's what you should do. Generalize. There is nothing special about 2 or 3. Try to figure out how the winning and losing states shift in different cases. What you will find is that the difference between losing states is always one more than the maximum allowed move for a player. I've glossed over a proof for why the difference between losing states was 3 or 4 in the above cases, but I believe the idea is intuitive and that was my purpose. A rigorous proof would follow from induction and exactly the same argument that we've made. Now I'll reiterate what I want you to take away from this example. First is the idea of simplifying a problem to make it easier to handle. Second is to use simple cases to find patterns which can be generalized to more complex cases. Third was the idea of winning and losing states. Now this idea is much more general than just application to games. It's about taking a large goal and then dividing it into smaller parts so that it's easier to work out the entire logic. The logic behind moving from one state to another was much easier to think about than to figure out an optimal strategy all the way from 17 balls or some other number. Let's take the previous game and modify it. So instead of one sack, we have two sacks and they have the same number of balls in them initially. In a move, a player can take out any number of balls but from exactly one sack. Whosoever is unable to make a move will lose. You can try out a few examples, see if you can figure out who can force it. Let's look at the simplest case. What happens if the sacks have just one ball? Well, the first player can either empty the first sack or they can empty the second sack. In either case, the second player can just empty the other sack. So this is losing for the first player. They can't make a move anymore. This is a losing state. Well, what happens if there are two balls in each sack? Well, the first player could either empty one of the sacks or they could remove one ball from one of the sacks. In the first case, the second player can just empty the other sack. So that's losing to the first player. In the other case, they realize that 1,1 was a losing state. So they can just take out one ball from the other sack and this is still losing to the first player. So this is a losing state again. You can try out more cases, but I'll try to extrapolate the general strategy from here on itself. Say there are n balls in each sack. The sacks are essentially the same, so it doesn't matter which sack the first player moves on. So that after this move, the second player can just copy the first player's move on the other sack. So after the second player's move, it looks like K, K. That is, the sacks are essentially the same. The second player can keep doing this. He can keep copying his opponent again and again and force the sacks to have an equal number of balls. In each move, the number of balls is decreasing, so the game must end. But with this strategy, the second player will not lose, which means the first player has to lose. So the second player can force a win. The idea which I wish to convey with this relatively simple example was that of symmetry. We exploited the symmetric nature of the sacks in the game to make sure that if our opponent has a move, then so do we. This ends up being very powerful in various games. Consider the following game. Vedant and Darsh are alternately placing white and black knights on a chessboard. Knights can only be placed on unoccupied squares and they can only be placed on squares which are not under attack by enemy knights. So, squares which are not under attack by opposite colored knights. Whosoever can not make a move loses. Just to make the situation clearer, let me consider an example. The first move is trivial. Say Vedant is going first as white and he plays on this square. Now, by the rules, Darsh cannot play on the square which is occupied by the white knight. So he can't play in this position. And he also can't play in any of the squares which are under attack by this white knight. So say that Darsh plays on this square. Well, now Vedant cannot play on the two occupied squares and he cannot play on the 8 squares attacked by this black. So the number of playable squares reduces for Vedant. At this point, pause the video and try to think, how does symmetry fit into the situation? Well, symmetry fits in because of the nature of the board. The board is symmetric and the rules of the game are uniform throughout the board and for both the players.
Now the simplest way to play symmetrically would be to copy the opponent's move across some imaginary axis, say this axis. But it's not entirely clear if this would work or not. So let's try and work through some of the logic. Say Vedant makes his first move and on some square. Doesn't really matter which one. Because Darsh can just make a move on the symmetric square because the white knight will never attack in a straight line. Say we're at some intermediate point in the game and Darsh has just moved and the board is symmetric. That is, the white and black knights are placed symmetrically above this axis. Say Vedant moves in that spot. That gives us three pieces of information. Firstly, the square which is symmetrically opposite to the spot has to be unoccupied because the black and white knights were placed symmetrically. Second, none of the black knights attack the square where Vedant is moved, simply because of the rules. But this tells us that the square which is symmetrically opposite is not under attack by any of the white knights. Well, any of the white knights which were placed just previous to this. So, excluding the knight currently placed, none of the white knights attack the symmetrically opposite square. Thirdly, this newly placed white knight does not attack the symmetrically opposite square because knights don't attack in a straight line. So, these three things, they tell us that the symmetrically opposite square is unoccupied and it's not under attack by any of the white knights. Which means that Darsh can move on the symmetrically opposite square, and after his move, the black and white knights will once again be placed symmetrically. As long as Vedant can move, Darsh can move symmetrically. Now, since the game must end, because the board only has 64 squares, and Darsh cannot lose because he is going to maintain the board in a symmetric state, well, then Vedant is not going to enjoy this game very much. So, let's recap. We did two problems where the winning strategy was to appeal to the symmetric nature of the game. The general strategy goes as follows. I've left the opponent in a symmetric position. So if they can make a move, then I should also have an analogous move which will be dependent on the symmetry of the game. Whenever you encounter such a situation which allows symmetry in terms of the rules of the game and the environment in which it is being played, like having two sacks or an even-sided square board, you should try and find such an argument. And such arguments, more often than not, end up being very intuitive. I mean, honestly, after the first few times I played chess, my first actual strategy was to just copy my opponent. Didn't work out very well, but the intuition exists. It seems to me as if copying is a built-in instinct. And this intuition can help you solve problems. The game we'll try today stems from a puzzle. You have 8 balls. They're identical in shape, color, texture, and size. 7 of them have the same weight. 1 of them is slightly heavier. You're also given a weighing balance, but you're only allowed to use the weighing balance twice. The goal is to use the weighing balance to figure out which of the balls is heavier. Try different strategies. Can you find a way to do it with just 2 uses of the weighing balance? The most intuitive way seems to be to split the 8 balls into 4 on each side. Now one of these has to be heavier because one of them has the heavier ball, of course. So say it's this side's heavier. Then we take these 4 balls and we split these into 2 and 2 and we use the weighing balance again. And once again, one of these will be heavier. So the heavier ball will lie in, say, these 2. But now we're out of moves and we have no way to differentiate between these 2 balls. So it doesn't work. What else could we do? At this point, we should try small cases. What if there's 2 balls? Well, we would need just one move, right? We could split them up into 1 ball each side and figure out which one's heavier. Well, what if we had 3 balls? There's no point in keeping 2 balls on one side and 1 ball on the other side because that side will always be heavier. The other ball is slightly. So the only other move is to put 1 ball on the right, 1 ball on the left, and leave 1 ball up. If the left side's heavier, well, we're done. If the right side's heavier, then we're done. With the third case, the weighing balance could be completely stationary, like the two balls could have the same weight, in which case the ball we left out is the heavier. So even with 3 balls, we just require one use of the weighing balance. This gives us some intuition regarding what's happening, though it might not be clear yet. But we can see that if we leave some of the balls out, we're able to gain more information. Let's go on and try more cases. So what happens if we have 4 balls? We could either put 1 on each side of the weighing scale and leave 2 balls out, or put 2 on each side of the weighing scale. No matter what we do, where we could end up with 2 balls after one use of the weighing scale, so we will need one more use. So if we get one more use, then we can just differentiate between the 2 balls by splitting them into 1 and 1. So for 4 balls, we need 2 moves. What about 5 balls? We can do something similar to the strategy for 3 balls. We keep two balls on each side and we leave one of the balls out. So after this move, we'll be left with either one ball, and if that's the case, then we're done, or one of the pairs of 2 will be heavier, in which case we'll take that pair, split it up into ones and measure which ball's heavier. So we can get 5 done in exactly 2 moves. At this point, let's go back to the original problem. The original problem had 8 balls and 2 moves. So we can do a similar thing by taking 3 on each side and leaving 2 out, because that's what we've been doing, dividing the number of balls into 3 close together groups and keeping the ones which have the same number of balls on either side. Now we could end up with 3 or 2 balls, which we can do in one move, as we've already seen. So for 8, we'll be done in 2 moves. Taking small cases showed us that leaving some balls out actually gives us more information, which would have probably been harder to figure out straight off the bat. So let's generalize. Given k balls initially, what is the minimum number of moves that we would need to figure out which of the balls is the heavier one? First, you should try more cases. Try to find a pattern, extrapolate, and make a guess about what this minimum number of moves could be. Then try to find an algorithm which shows that if you're given these number of moves, that you can actually find the ball, that you can guarantee that you will find the ball. Second, show that this is a minimum, that if you're not given as many moves, then it's not possible to guarantee that you'll find the ball. Here we'll see another important idea, that is induction. It's especially useful when you want to show that something is true for all natural numbers. This might be the only time I state something as a formal axiom, but induction is fundamentally tied into our intuition, and the statement goes as follows. Let P of X be a property which is either true or false for all natural numbers. We're going to take a starting point. This is called a base case, which is 0. So if P of 0 is true, and for all natural numbers n, we can show that given P of n is true, we can prove that P of n plus 1 is true, then P is going to be true for all natural numbers. The statement might feel heavy, but it's actually very intuitive. What it's saying is that you have a property for which if P of n is true, then you should be able to show that P of n plus 1 is true. When you take this and you start off with P of 0 being true, you use the property to show that 1 is also true, P of 2 is also true, and so on. Doing this, you're going to go through all of the natural numbers. So P has to be true for all of the natural numbers. We're just using the fact that given P of n is true, we're able to show that P of n plus 1 is true. From our test cases, we know that if we're given 1 ball, then we need 0 moves. If we're given 2 or 3 balls, then we need just 1 move. If we're given 4, 5, 6, 7, 8 or 9 balls, then we need just 2 moves. In the case for 9 balls, we can just put 3 balls on each side, leave 3 out, and then we'll shortlist 3 after this one, which can be done in 1 move. So for 9, we'll only need 2. The intuitive idea here is that the shifting moves is always happening at a power of 3. So 1, 3, and 9. We should try more cases, especially 27, to see if we're right. I'll leave that up to you so that you can try and convince yourself that this is a very reasonable argument to me. Say we start off with k balls initially. We're going to take two consecutive powers of 3 such that k lies between them. That is, 3 to the s is less than k is less than or equal to 3 to the s plus 1. You can always do this. For example, 15 is between 9 and 27. Just think of logarithms. So the conjecture is that the minimum number of moves we would need to find the heavier ball among these k balls is s plus 1. This is the conjecture. Now, to prove it, we'll need to do two things. First, we need an algorithm to show that if we actually have s plus 1 moves, then we can find the heavier ball. I leave that up to you to make that argument as rigorous as possible, and you can try to find the exact moves. Here, I'll try and prove that this is the minimum. So we will use something called strong induction, which has the same basis as the induction we've seen. It essentially says if we're given, using the fact that P of n is true for all n less than or equal to k, if we can show that P is true for k plus 1, and we also have a base case where P of 0 is true, then P is going to be true for all natural numbers. So we'll use this. If we have one ball, so 1 is between 1 by 3 and 1, which are powers of 3. So 3 to the minus 1 and 3 to the 0. So the conjecture would say that we need 0 moves to, in the case we're given one ball at the start, which makes sense because even though we can't compare it to something else, we are assuming that in every case we have a special ball. So in this case, this must be the special ball and we don't need any moves to find. Now that we have the base case, say that the conjecture is true for all natural numbers less than k. We want to show that it's also true for k. Well, say that 3 to the s is less than k, and which is less than or equal to 3 to the s plus 1. Now, when making a move on k, there is no point in putting an unequal number of moves of balls on either side of the weighing balance. So say we put x on each side of the weighing balance and leave out k minus 2 moves. After this move, we'll either know that the ball is in one of the x groups or the k minus 2x groups. The thing is that we must guarantee a win. So we must be able to win even in the worst case scenario, which would be that we shortlist the maximum of these two numbers. We want to show that even when we shortlist the maximum of these two numbers, we can guarantee one. Now the max of these two will be greater than k by 3, greater than or equal to k by 3. Why? Say they're not. What would that mean? That would mean that x is less than k by 3, because we know that the max is not greater than or equal to k by 3, and that would also mean that k minus 2x is less than k by 3. The second inequality simplifies to k by 3 less than x, which contradicts the first inequality that we've taken, which means that this assumption is wrong and the max has to in fact be greater than k by 3. That's even in the worst case scenario, the number of balls that we will shortlist will be greater than k by 3. Say a balls are shortlisted. Well, then a is going to be less than k, and so by the assumption that we made, the conjecture has to be true for a. Secondly, a is greater than k by 3. This we've already shown. A is also less than k, which means that it's greater than 3 to the s minus 1 and less than or equal to 3 to the s plus 1. So, by the conjecture, the minimum number of moves required for A is either S or S plus 1. Now, that means to solve from K, we are going to need at least one more move. So, at least S plus 1 moves are required to solve all the way from K and find the heavier move. Let's go over what we just did. We saw a new situation,
And we tried a very intuitive idea, which was to split into halves so that in every move you're shortlisting one. It didn't work. Sometimes your intuition will throw you into rabbit. Our saving grace was trying small cases. Once again, it's easier to find flaws within your own intuition and to get a better understanding of things when you get rid of unnecessary complications. The game is essentially the same for 3 balls, 8 balls, or 2357 balls. Doesn't matter. So we try this simplest case we can see and see if we can actually do something about it. The other thing we did was use these ideas from our simpler case and extrapolate them to a more general setting and see if they're useful enough. Like here, what we saw was that it's better to divide the balls into 3 piles instead of 2, which ties into the fact that the weighing balance actually has 3 states: right heavy, left heavy, or equal. We can let all 3 of the states give us information, that is, imply which pile the heavier ball is in. The last thing we did was find a generalization and use induction to prove that our algorithm is optimal. That is, any other algorithm to play the puzzle is as good as or worse than ours. This often ends up being the most technical and has its own quirks, which I have not focused on because the video isn't about proof writing. It's about having intuition about what to do when you're in a new and difficult situation. The contents of this video will end up being a lot more technical, meaning that we will look at a complicated setup with an intricate set of winning and losing states to analyze. Let's go over the game rules. Arnaud and Bibin play the following game. They have an integer which is greater than 1 and less than or equal to 1000. The players move alternately, performing operations on the number, and Arnaud goes first. Now, this game is different from the games we've seen up till now because the set of rules for the players are different. So, Arnaud can divide the number by 2 if the number is even, or he can add 4 to the number. Bibin can multiply the number by 2 if the number is odd, or subtract 2 from the number. Arnaud wins if the number becomes 0 or 1, while Bibin wins if the number exceeds 1000 or the players make 100 moves each without the game ending. Now, though the setup is quite elaborate, I would suggest that you try to solve the entire game by yourself because the solution relies completely upon ideas we've already visited. Since the set of rules for both the players are different, we're going to be looking at A winning and B winning states. That is, assuming Arnaud starts, who can force a win? We'll have to keep track of 2 things: the current number and the number of moves elapsed. That's because of the second winning condition for Bib. Now, straight off the bat, we can categorize 0 and 1 as A-win by definition. What about 2? Well, Arnaud starts, so 2 is even. He can divide it by 2, get 1 and wins. This is A-winning. We consider the next case, that is 3 at the start. Arnaud is forced to add 4 because 3 is odd. At this point, Bibin has 2 options. He can either multiply 7 by 2 to get 14 or subtract 2 to get 5. Which one's better? At first glance, it may seem like 14 is better because it's a bigger number, but we can't just tell by looking at it. So let's look at how the game progresses. From 14, Arnaud could divide by 2 again to get 7 or add 4 to get 18. Now, getting 7 again is essentially this game state 2 moves back, and Arnaud is just losing 2 moves, which is bad for him. So in this case, we can safely assume that he would add 4. What about the other case? Well, 5 is odd, so Arnaud is forced to add 4 and give Bibin 9. Do you see a pattern? See 3, 7, 5, 9. The idea is that when the numbers are odd,
R0 is restricted. He's forced to keep adding 4 to the number. We can use this. So Bibin can just subtract 2 and R0 will once again be forced to add 4 to 7 and get 11. So that after every 2 moves, the number increases by 2. If we keep doing this, either of two things happen. Either the number becomes greater than 1000 or the players use up the 200 moves. In either case, this is D-win. Now this can easily be generalized. That is, say we start off with an odd number. Now R0 will be forced to add 4. Bibin must make sure that R0 gets an odd number, so subtracts 2. Now this repeats, and after every 2 moves, the number is going to increase by 2 because R0 is forced to keep adding 4. Either of two things happens. Either the number becomes too large, that is greater than 1000, or the players run out of moves and Bibin wins. Since we've already categorized all of the odd states, let's look at what happens if we have an even number at the start. So take 4. R0 can either divide by 2 or add 4, give 2 and 8. Now if Bibin gets 2, he has no option but to subtract 2. So he subtracts 2, gives 0 and R0 wins. So this is winning for R0 and the first strategy is optimal. Now we can use hints for the way we dealt with the odd case. R0 was restricted when given odd numbers and that was what gave Bibin a winning strategy. So now Bibin is restricted when given even numbers. Can we use that to make a strategy for R0 or does Bibin still win? Let's see. Now consider the case where there's 6 at the start. There's no point in dividing by 2 for R0 because Bibin would just multiply by 2 again and R0 is losing moves for no reason. So the only other option is to add 4. Now if R0 adds 4, we get 10 and Bibin has just one option which is to subtract 2 and give 8. At this point R0 can divide by 2 because he'll be leaving Bibin with 4, not some odd number which he could multiply to waste moves. So he leaves Bibin with 4 and now Bibin is forced to subtract 2. So Bibin subtracts 2, gives 2 and then R0 can divide by 2 to get 1 and this is winning for R0. So the strategy seems to work, but we need to generalize this. The idea is to leave Bibin at even numbers. So say we start off with some even number, 2 times x. In case x is even, then R0 can just divide this number by 2 because this will leave Bibin with x which is even and Bibin will subtract, it's a forced number. So R0 gets an even number again. In the case where x is odd, we can't just divide. So the other move is to add 4. Now Bibin will be forced to subtract 2, after which we can divide because since x is odd, x plus 1 is even. Now Bibin is forced to subtract 2 and we get x minus 1. So in at most 4 moves, R0 can reduce this even number to another even number which is less than half of this number. And since we're getting even numbers, he continues to do this. Now the initial number is less than or equal to 1000. So it's at most 1000, which is less than 2 to the 10. That means we're not going to need to halve more than 10 times. So with at most 40 moves, R0 can get the game to either 0 or 1. You would then think that even numbers are evening, but the issue is that we're adding 4 in our algorithm. So while this is not an issue for the smaller even numbers, we need to make sure that for the larger ones, we're not somehow exceeding 1000 and letting Bibin win. For 1000, it's straightforward. We just divide by 2 and then Bibin subtracts 2. So there's no issue. What about 998? Well, you cannot add 4 here because 1002, Bibin wins. But if you divide by 2, you get an odd number. So Bibin can just multiply this by 2 again. And now R0 is stuck in this cycle which he cannot get out from. So once they actually get through 200 moves, Bibin wins. For the other even numbers, this does not happen. They won't exceed 1000. In the end, we get that if n is odd, or 998, then Bibbing wins. Otherwise, Arnold wins. And that's the result. With this game, I have not gone over any sort of new machinery to solve the problem. The idea was to show a more dynamic setup where the ideas that we've already seen, especially winning and losing states, take center stage. Even with such an elaborate setup, the very first step was to go after the tractable winning and losing states. And if there's any sort of motivation to look at the even and odd states separately, it lies in the parity constraints on the rule sets for the players. In this video, I'd like to discuss a game which is quite popular in combinatorial game theory. It's called the game of chalk. Here's how it goes. Alice and Bob have a chocolate bar which is made up of numerous squares. In a move, the players move alternately with Alice going first. And in a move, the players choose a specific square and eat all of the squares to the right and bottom of the chosen square. No one's going to change the orientation of the chocolate while playing. And the point is that the top left square of the chocolate is poison. So whoever eats that square loses. Now we can break the problem down into two parts, two cases. The first one being the chocolate is itself a square, that is m by n. The second, the chocolate's a rectangle, m by n. We're going to figure out who has a winning strategy in each case. Let's take an example. You have a 3 by 4 chocolate, right? Say Alice moves on this spot. Well, that leaves an L shape in the board. Now, Bob could eat off one of the arms, right? He could do that. But that's a mistake because now Alice can eat all of the non-poison squares and Bob will be forced to eat the poison square. That's one example. You can try out a few more examples and see if you can come up with a winning strategy. Let's look at case A. We have an m by n chocolate. Now, the thing is, I don't see what to do. Because there are so many possible choices, it's nearly impossible for me to figure out the optimal strategy. So, to get rid of the number of choices, we look at small cases, one by one. Well, this is trivial. The soul chocolate is poison, so Alice is forced to eat it. Alice loses, Bob wins. So this is B winning. Consider the 2 by 2 case. Alice has 3 different possible moves. She can move bottom right, top right, or bottom left. Notice that moving top right and bottom left is essentially the same move because the chocolate is symmetric about the diagonal. So moving top right is essentially the same as moving bottom left and a volt flipped about the diagonal. Also see that these two are in fact losing for Alice because Bob makes the one non-fatal move after which Alice will be forced to eat the poisoned chocolate. Well, in that case, the only other option for Alice, if she wants to win of course, is to eat the bottom right square. It leaves us with this L shape, after which Bob has 2 possible moves. Bottom left, top right. Alice can now make the non-fatal move, after which Bob is forced to eat the poison chocolate. So we can see that Alice has a winning move and thus the 2 by 2 case is A winning. Let's consider the 3 by 3 case. Thing is, in this case, it would be extremely tiresome to work through all of the cases. There's just too many possible choices. So we try another approach. See, the chocolate is itself symmetric. Can we use this inherent symmetry to somehow find a solution? Let's look at the 2 by 2 case with this perspective in mind. The winning move for Alice in this case was to eat this square, which left us with a symmetric L shape on top. After which, no matter where Bob moved, Alice could just move on the opposite side of the L and win. The entire argument is symmetric. Let's look at the 3 by 3 case with this perspective in mind. There's 2 moves which lead to a symmetric figure. The first one is to chomp at the bottom right square. The other move is to chomp at the center square. Let's consider both cases. In the first case, where Alice chomps at the bottom right square, Bob would want to follow a similar strategy. To say now Bob chomps at the center square. What happens? Well, Alice is left with this symmetric L shape. And now, no matter which arm Alice moves on, Bob makes a move on the opposite arm. It's a symmetric argument. It works because a player can affect exactly one arm in their move unless they're eating the poisons. So in this case, we see that Bob will win because as long as Alice has the move, Bob has it. In the other case, Alice is leaving the L shape. So now whatever move Bob makes, Alice can make that same move on the opposite arm of the L. So Alice wins. So we can see that the general strategy for Alice is just to leave a symmetric L shape after her first move, and then she can just copy Bob's moves. So in the general M by M case, Alice can achieve the L shape by just moving on the 2, 2 square. And we see that Alice is winning for a symmetric chocolate. That is, in the first case, Alice always wins. Let's look at the second case, where it's a general rectangle and M is not equal to N. Pause the video and try small cases. Say try 2 by N, 3 by N. Can you find a winning strategy? Can you find a generalized winning strategy? If you can, go to a professor, get it verified and publish. See, although we know who has a winning strategy in this game, we have no idea what that winning strategy in fact is. The general problem is open. It's unsolved. The only solved cases are 2 by N, is just a rectangle of width 2, and M by M, a symmetric square, the case we just saw. This might seem weird. How do we know who's going to win if we don't even know what the strategy is? Here comes the idea of a do-nothing move. While it may seem like I pulled this out of the net, which I kind of did, mathematical epiphanies don't always have a reason behind them. Sometimes they just happen. You won't always know why. So let me at least try to explain the idea. See, for any finite game with 2 players and no draws, one of the players can always force a win, dependent on what the initial state of the game is. Why? Well, consider any starting state, right? From this state, there's a fixed possible set of states we can go to. We can make branches to all of them. From each of those, we can make branches to every single state we can go to from those states. And I can keep doing this. I keep doing this, and every single sequence of moves has to end somewhere because the game is finite. It can't go on forever. And each of these ending points, well, one of the players must have won and the other must have lost because there are no draws. So I'm going to label each of these points as winning and losing. They're winning if the player whose turn it is has won. And they're losing if the player whose turn it is has lost. It's relative to whose move it is and what state they're in. Now using these labels, we can go up the tree. We can look at the nodes which are connected to the lower nodes and we can label those nodes with our rules we've made in previous videos. See, if from a state there is some move which goes to a losing state, well, that state is winning. And if from a state all moves go to winning states, then that state is losing. Using these two rules, we can uniquely identify each node as winning or losing. We can keep doing this up the tree until we can label the very initial node as winning or losing. Now consider a special state A. Why is it special? Because it has a do nothing move. What does that mean? So a do nothing move essentially has this property that, say I make the do nothing move on A and it takes me to A dash. Well, if there is a move from A dash to B, B is not A, then there is a move from A to B. That is just what the do nothing move is. I call it the do nothing move because essentially we're wasting a move and going from A to A dash. Well, we could have just gone to B directly. This is relevant because now we ask the question whether A is a winning state or A is a losing state. Assume that A is losing. What happens? Say A is losing. Well, all moves from A must lead to winning states. That's a general rule. Right, that means A dash is a winning state because the do nothing move takes us from A to A dash. But now from A dash there is some move which takes us to a losing state.
And this cannot be A, because then we'd have an infinite loop and the game is actually finite. But there's a move from A to B, because A to A dash was do nothing move. But A was a losing state, so all moves from A must go to winning states, while B is a losing state. It gives us a contradiction, which means that our initial assumption must be wrong and A is not a losing state. And we get that A is winning. It tells us that any state which has a do nothing move is winning. Why is this relevant? Because the game of chomp for an m by n rectangle has a do nothing move. What's the move? Well, it's the bottom right square. Let's think it through a little. This move sends us to this chocolate bar with one square corner. The point is, any move you can make on this chocolate, you could make on the initial chocolate and you'd get the same result. Because any move on the initial chocolate gets rid of this bottom right square. So it's kind of irrelevant to get rid of it just as it is and not do anything else with it. So with everything else we've already done, we can say that Alice can win from an n by n rectangle as long as she plays optimally. We just don't know what optimally is. What you need to take away from this isn't that we use symmetry, but the fact that because we had seen such ideas before, it was easier for us to spot that symmetry might be useful. The other thing is that while the proof involving the do nothing move is very fascinating, at least to me, the takeaway isn't that idea. Rather, it's the fact that sometimes the solution to a problem just needs you to step away from it for a while and let your subconscious deal with it. Epiphanies have happened in kitchens, bathrooms, dreams. Someone might have had one while rock climbing. The thrill and emotion induced by that moment is what draws me to mathematics. And I think it's what draws a lot of other people to mathematics also. And this is why I personally believe that the best way to teach someone mathematics is to let them solve problems and let them have ideas of their own.